Bismillahirrahmanirrahim. Assalamu alaikum dear students. I am Arif and I welcome you all to lecture number 27 on the subject of computer organization and assembly language programming. This post-mid part of the course actually deals with the assembly of the x86 64-bit microprocessor. Well dear students, in the last session we started with the evolution or the history of Intel microprocessors. We discussed as to how Intel Corporation started with their first 4-bit microprocessor and how the hardware designers improved the microprocessor performance by incorporating various hardware and software techniques. In the last session I promised that I will take a separate session on the architecture of pipeline processors. So I am fulfilling my promise today. And today's session will be an effort to give you an overview of pipelining and how it helps in improving the performance of today's microprocessor. Well, this slide shows agenda of today's session. We will start with the CPU performance equation. We'll have a brief comparison between single cycle and multi-cycle CPU architecture. Then we will have a discussion on some very basic concepts of pipelined microprocessors. And finally, we will conclude today's session with a comparison between the CISC and the RISC architecture. We have a lot to do today, so let's start playing. Let us first understand the CPU performance equation and see what are the factors on which performance of a CPU depends. Well, dear students, CPU performance equation analyzes execution time as a product of three factors that are relatively independent of each other, namely the instruction count, the clock cycles per instruction, CPI, and the clock cycle time, CC, or maybe CCT. Well, this instruction count means number of assembly instructions in the program to perform a specific task. And the CPI means number of cycles required to execute one assembly instruction. And this clock time means the number of times the CPU clock ticks per second. For example, a clock rate of 1 megahertz means the CPU clock takes 1 million times per second. And since one instruction takes a specific number of clock cycles to execute, therefore the clock time has a direct impact on CPU performance. So to sum up, let me say that the CPU designers need to lower the value of these three factors in order to improve this CPU performance equation. Well, if we lower the instruction count by adding more complex assembly instructions, this will increase the other two factors, that is the CPI as well as the clock time. And if we reduce the clock cycle time by increasing the frequency of the CPU clock, that is by designing small and high speed transistors, the hardware will consume more power and more heat will be generated. And the last option left is reduce CPI, that is cycles per instruction, by using techniques like thread level parallelism, pipelining, superscalar CPU design, and so on. Let us understand this CPU performance equation with the help of an example. And suppose that there is a program that takes 1 billion instructions to execute on a processor running at 2 gigahertz. And also suppose that 50% of the instructions take 3 cycles to execute completely, 30% takes 4 clock cycles, and the remaining 20% takes 5 clock cycles to completely execute. The question is, what is the overall execution time of the program? So if we put up all these values in this CPU equation, we get the execution time to be 1.85 seconds. I hope this makes sense to you all. The instruction count is 1 billion 10 raised to power 9. The CPI is of course 50% of the instruction execute in 3 clock cycles, 30% execute in 4 clock cycles, 2% execute in 5 clock cycles, so overall becomes 3.7. And since the clock time is 2 gigahertz, so 1 over 2 gigahertz comes out to be something like this, and the final time is this. Okay. Well, dear students, before I talk about pipelining, let me set the stage right by letting you know the difference between a single cycle and a multi-cycle CPU architecture. Well, let us talk about the single cycle CPU first. A single cycle CPU executes each instruction in exactly 1 clock cycle. That is, the CPI of a single cycle CPU is 1. Irrespective of how simple or how complex an instruction is, it will take 1 clock cycle to execute. So the clock cycle of the CPU has to be large enough to completely execute the most complex or the slowest instruction in the ISA. Well, the disadvantage of a single cycle CPU is that it must operate at the speed of the slowest instruction. That is, the clock cycle is quite large. And the advantage is that it is easy to implement. Dear students, let us suppose that we want to design a CPU whose instruction length is 16 bits. Instruction can have 2 register operands or a single memory operand. 4 bits are reserved for opcode and 5 bits for register address. So given this scenario, a question is, how many CPU registers can be accommodated in this architecture and what can be their size? Please stop the video and try to answer this question. Dear students, as there are 5 bits reserved for register address in the instruction, so 2 raised to the power 5 or 32 registers can be accommodated. And as far as the size of each register is concerned, they should be of the same size as the word size of the main memory, that is 16 bits. Let us try to give the answer to this question now. How many main memory locations can be addressed in this architecture? Once again, please stop the video, think on it, and then move ahead. Well, dear students, as mentioned over here, an instruction has 4 bits reserved for the opcode in case of a single memory instruction. So the remaining 12 bits can be used for the memory operand. Hence, 2 raised to the power 12 or 4K memory locations can be addressed in this architecture. And below is a diagram showing the data path for a single cycle CPU. The main components involved in the data path are the instruction memory, the register file, the ALU, and then the data memory. Let us see how an add instruction that sums up the contents of 2 registers is executed on this architecture. First of all, fetch. An instruction is fetched from the location of the instruction memory where this program counter is pointing. Then is the decode. In the decode step, different parts of the instruction are decoded. For example, these 2 5 bits are sent to the register file to get the operands of the instruction. These 4 bits are sent to the ALU to specify the operation, which is add over here. Then in the get operand phase or step, the 2 5 bits registers come up to the ALU over here. Then in the execute phase, the ALU carry out the specific arithmetic operation, in this case the add operation. Finally, in the write back or the result writing stage, the result is written to the destination register over here, and maybe to the memory as well. And of course, I forgot that this program counter is also incremented or set to the address of the next instruction to be executed in the initial part of this discussion. My dear students, in case of a single cycle CPU, all these steps, that is fetching instruction from the instruction memory, decoding of the instruction, reading the operands from the register file or the data memory maybe, executing of the operation by the ALU, and writing of the result to the register file or the data memory. All these steps are performed in a single CPU cycle, which has to be large enough to deal with the most complex instruction in the ISA. Okay, so having said that, let us now talk about the microarchitecture, that is the data path and control of a multi-cycle CPU. Wow. Well, the key difference is over here is that in this multi-cycle CPU architecture, the execution of a single instruction will take multiple cycles to complete. So that is why the data path is a bit complex. The key change, as you can observe, is the introduction of temporary registers to hold the outcomes that are produced by each cycle. For the time being, just ignore the details and focus on these colored boxes. This IR represents the instruction register used to hold the instruction for decoding. A register is needed as we are using a single memory for both data and instruction over here. This MDR represents the memory data register used to hold the data value returned from the memory. These R1 and R2 are temporary registers used to temporarily hold the register values read from this register file. And finally, this ALU out is used to temporarily hold the result calculated by the ALU. Let's now understand how this data path works by executing a simple add instruction, add R5, R1, R2, assuming that this instruction will read the contents of R1 and R2, perform an addition on the contents, and write the result back in register R5. Let's see it step by step or cycle by cycle. Well, in cycle 1, the instruction will be fetched and the program counter will be incremented. So the contents of program counter register are given to the memory, and the instruction is temporarily saved inside the instruction register. And this is also a good time to increment the contents of the program counter to point to the address of the next instruction to be executed in sequence. So the existing contents of the program counter are given to the ALU, and it is incremented and written again so that it should point to the next address. And the RTL is also given over here. The contents of memory pointing to by PC are read and placed in IR, and the program counter is incremented by 1. By 1 over here I means the size of the program counter or size of the instruction. Okay, let's talk about the cycle 2. In the second cycle, the instruction in the IR register over here is decoded. The control unit will take a look at the opcode in order to decide what should be happening in the next cycle. Well, since both the source operands of this add instruction are registered, so some bits of the instruction will be sent to the register file to read the first operand and will be placed in R1. And similarly, some bits of the instruction will also be sent to the register file to read the second operand and will be placed in R2. So at the end of the second cycle, the temporary registers R1 and R2 are loaded with the operands. And this is the RTL shown over here. And what happens after cycle 2 depends on the actual instruction. Since we have already fetched the operands in cycle 2, so cycle 3 is going to execute. This is the execute cycle. Since this is an add instruction, so the two operands R1 and R2 are given to the ALU. The control tells the ALU to perform the specific operation, which in our case is the add operation. And the ALU performs the operation and stores the result in the temporary register ALU out. Finally, in cycle 4, the result is written inside the register file in the appropriate destination register. From here, it will move to the appropriate destination register, which will be 5 in this case. So dear students, now is the time that you give me the answer to a $100 question. And that is, why CPU designers prefer a multi-cycle CPU over a single cycle CPU? While we can see that a multi-cycle CPU has quite a complex data path. Well, dear students, the clock time of a single cycle CPU is quite large, as we have seen, large enough to complete the longest instruction in the machine. We have seen the CPU performance equation as well. And one of the way to improve the CPU performance is to reduce the clock time or increase the frequency. So multi-cycle CPUs give us two advantages. First is, it helps us in reducing the clock cycle time. And another advantage is reuse of the functional units. For example, this ALU and this register file are free in the first cycle, that is during the fetch phase. Similarly, this memory is free during the execute cycle, and so on. Okay, dear students, from a multi-cycle processor, let us now move to another technique that is used in almost all processors these days, called pipelining. And pipelining is a technique where a stream of instructions can be executed by overlapping the fetch, decode, execute, and write back phases of a multi-cycle processor in order to increase the overall throughput. Let me describe the concept of pipelining by giving you an illustration of a laundry system. Over here on the x-axis we have the time progressing from left to right, and over here on the y-axis we have the laundry orders. Suppose we have some clothes to wash. Let it be task A, and also assume that we start this task at time 6 p.m. Okay, we took 30 minutes for washing these clothes, 30 minutes for rinsing or drying these clothes, and 30 minutes for folding or ironing the clothes of this task. So task A get finished at 7:30 p.m. It took 1 hour 30 minutes. Let the next bundle of clothes be task B, and we follow the same steps. That is 30 minutes for washing, 30 minutes for rinsing, and 30 minutes for folding. So the task B get finished at 9 p.m. The same sequence is followed by the system, laundry system, for washing of the clothes inside the task C, which finish at 10:30 p.m. and then D, which finish at 12 p.m. And finally all the 4 tasks are completed at 12 p.m. That is, the total time taken is 6 hours. Task A completes at 7:30, task B at 9:30 or rather 9, task C at 10:30, and task D at 12 p.m. Well, my dear students, if you closely observe, when this task A was being executed from 6:30 to 7 p.m. That is when the clothes of task A were being dried or rinsed. This washing unit as well as the folding unit were free. And the same observation can be made in this entire laundry process. So let us utilize all the three functional units by using the pipeline technique in this laundry system. And once again, over here in this slide, I've tried to show an illustration showing the same laundry system, but this time it will be pipelined. The time is moving from left to right, and these are the tasks. Well, from 6 p.m. to 6:30 p.m. we are washing the clothes of task A. From 6:30 to 7 p.m. the clothes of task A are being rinsed, and since the washing unit is free, we have also started washing the clothes of task B simultaneously. And similarly, from 7 to 7:30 p.m. the clothes of task A are being folded or being ironed. The clothes of task B are being rinsed, and the clothes of task C are being folded. Well, during this half an hour, during these 30 minutes, you can observe that all the three functional units of this laundry system are being utilized. And of course, the task A gets completed at 7:30 p.m., which is the same time as in case of the non-pipeline laundry system as well. Well, dear students, this process goes on. You can observe that the task A gets completed at time 7:30. The task B gets completed at time 8. The task C gets completed at time 8:30. And the task D gets completed at time 9. Total time taken to complete these 4 tasks in this laundry pipeline is 3 hours, whereas the time taken to complete the same 4 tasks in the non-pipelined laundry system was 6 hours. Although every task is still taking 90 minutes, note that task A has taken total of 90 minutes, task B has taken total of 90 minutes. So every individual task is still taking 90 minutes, but the overall throughput of the system is increased. Now a $100 question is, if these functional units do not take the same amount of time, that is 30 minutes to complete, we may need to temporarily store the output of this washing unit before giving it as input to the rinsing unit. So where to store the output of the previous unit? So we need to have temporary place over here in between these 2 stages and in between these 2 stages. Okay, so well, dear students, this slide shows you a n stage pipeline. The output of each stage is connected to the input of the next stage, and in between these 2 stages we need to have a temporary storage area called the interface or the intermediate register that stores the output of each stage before making it input of the next stage. So if this is a n stage pipeline, we need to have n-1 registers or latches in between. Moreover, let me say that there can be 2 categories of pipeline. The first is the even pipeline, in which all the stages have same latency. That is, stage 1 is going to take, let's suppose, 3 microseconds, stage 2 is going to take 3 microseconds, stage 3 is going to take 3 microseconds, and so on. And the other category is uneven pipelines, in which stages can have different latencies. And both have their own pros and cons. I leave this topic of discussion for the computer architecture course and move ahead. My dear students, another question that might come to your mind is uh, by increasing the depth of this pipeline, that is, by increasing the number of stages of this pipeline, will the performance always increase? And does this have an upper limit? Well, I'm just leaving these pointers in your mind so that you can get the clarification of these questions in your upcoming course, that is the computer architecture course. So the main point is we have stages of pipeline, and in between each stage we have intermediate or temporary holding areas called the registers. Well, dear students, in computer science, pipelining can be defined as the process of arrangement of hardware elements or functional units of CPU such that its overall performance is increased. A pipeline processor allows multiple instructions to execute concurrently, while each instruction uses a different functional unit in the data path. The microarchitecture of a 5-stage pipeline processor MIPS R3000 is shown over here. We have the instruction fetch phase, in which the instruction is fetched from the memory. This is the stage. We have the instruction decode and the operand fetch phase. Then we have the execute phase, execute the instruction or maybe calculate the operand address. Then we have the mem stage, in which we may need to access an operand from the data memory. And finally we have the write back stage, where the final result is written back to some register. Dear students, please do note that this is a 5-stage classic RISC pipeline, having the stages named as instruction fetch, instruction decode, execute, memory, and write back. Do note the 4 latches or temporary storage areas in between each stage. This one, then this one, then this one, and then this one. Okay, let me give you an illustration of an instruction pipeline of MIPS R3000 having a 5 uniform pipeline stages. By uniform I mean every stage will take equal amount of time, and I'm also assuming that every instruction will pass through all the 5 stages to complete its execution. Well, in this table the clock cycle progresses from left to right along the x-axis. And suppose the program consists of 6 instructions which will appear over here along the y-axis. And in case of a non-pipeline multi-cycle processor, each instruction would have taken 5 clock cycles to complete. So a program of 6 instructions would have taken a total of 30 clock cycles in case of a multi-cycle processor, non-pipelined. And let's see how much performance gain we can achieve if we make this architecture pipelined architecture. Okay, at cycle 1, this is the clock cycle 1. We have the first instruction over here. It comes to the instruction fetch phase. At clock cycle 2, the instruction 1 will go to the decode phase, while we can always have the instruction 2 in the instruction fetch phase. At cycle 3, instruction 1 will go to the execute phase, instruction 2 will go to the decode phase, and we can have instruction 3 in the fetch phase. And similarly, at cycle 4, we can have the instruction 1 in the memory phase, instruction 2 in the execute, instruction 3 in the decode, and we can have another instruction 4 at cycle 4 inside the fetch phase. And similarly at cycle 5, the same process will move on. My dear students, since this is a 5-stage pipeline, you can observe that after this 5th cycle, this instruction 1 gets completely executed. So first instruction completes at clock cycle 5. Note that at clock cycle 6, instruction 2 is completely executed. So at clock cycle 7, instruction 3 gets completely executed. Clock cycle 8, instruction 4 goes out. Clock cycle 9, instruction 5 goes out. And finally at clock cycle 10, instruction 6 is completely executed. So instruction 6 completes at clock cycle 10 instead of clock cycle 30 in case of a non-pipeline processor. So for a k-stage pipeline, nth instruction will complete in k plus n minus 1 clock cycle. In this scenario, 6th instruction completes in a 10 clock cycle. The aim of pipeline processor is to maintain a CPI of 1. So we get a CPI of far less than 1. But if we take an example having 1000 instructions, using the same formula, you can check that in case of 1000 instruction, a 5-stage pipeline will complete the 1000 instruction in 1004 clock cycles, which is quite close to a CPI of 1. My dear students, if you want to calculate the speed up achieved on a pipeline processor, you can use this formula. Clock cycle taken on a non-pipeline processor divided by clock cycle taken on a pipeline processor. This was 30 and this is 10. So after this pipelining, the speed up that is achieved is 3 times. So this is 3 times faster as compared to the non-pipeline processor. In reality, such a performance cannot be achieved, but however, we do get the performance. We do get better performance. And why we cannot achieve the perfect CPI of 1, I will talk about this in upcoming slides. Well, dear students, the cycle time of a pipeline processor is of course dependent on 4 factors. First is the cycle time of non-pipeline version of the processor. Then we need to know the number of pipeline stages, the latch latency, and how evenly the data path logic is divided among the stages. And if I want to compute the cycle time of a even pipeline processor, knowing the cycle time of a non-pipeline processor, this is the formula in which I divide the cycle time of a non-pipeline processor with the number of stages plus the latch latency. And in case if we want to calculate the cycle time of an uneven pipeline processor, then simply we add up the latch latency to the cycle time of the longest pipeline stage. I hope this makes sense to you all. Well, my dear students, in a pipeline processor, ideally we expect a CPI value of 1 and a speed up equal to the number of stages in the pipeline. But there are a number of factors that limit this. The problem is that there exist hazards inside an instruction pipeline. And pipeline hazards are actually situations that prevent the next instruction in the instruction stream from being executing during the designated clock cycle. And there are 3 different classes or types of pipeline hazards: structural hazards, data hazards, and control hazards. Let me talk about them one by one. First of all, structural hazards. Well, structural hazards occur when multiple instructions are trying to access the same resource, like the caches, memory, or I/O devices, in the same clock cycle, of course. Structural hazards arise because there is not enough duplication of resources. For example, consider this pipeline diagram. Instruction 1 at clock cycle 4 is reading the memory. Instruction 4 at clock cycle 4 is also trying to fetch an instruction from the memory. So we have a structural hazard. Over here I am assuming that we have a single memory for both data and instruction. So what is the solution to the structural hazards? One of the solutions to structural hazard is to add more hardware, which is of course an expensive solution. And another solution is wait or stall the pipeline. For this to work, there must be a mechanism to detect the hazard and then to stall. It is simple, less expensive solution, and however it increases the overall CPI. So this pipeline diagram shows you the example of this. In the previous diagram we have seen that at clock cycle 4 instruction 1 is also accessing the memory and instruction 4 is also accessing the memory. So at clock cycle 4 I have not started instruction number 4, rather I have started instruction number 4 at clock cycle 5. So instruction 1 is accessing memory at clock cycle 4 and instruction 4 is accessing memory at clock cycle 5. So now there is no structural hazard. So this is a no operation instruction. So what we need to do is we need to add hardware inside the CPU which will detect the structural hazard at this clock cycle 4. Then there need to be a mechanism to stall the pipeline by placing a no operation instruction at the appropriate clock cycle. So in this scenario, a stall of one clock cycle will do the job. Note that due to this structural hazard, the program completes in 11 clock cycles. Well, the second class of pipeline hazards are data hazards, which occur when an instruction depends on result of a prior instruction still in the pipeline. Well, data hazards can further be classified as data dependencies or true dependencies or simply raw, that is read after write hazard. Let me explain this with the help of an example. Well, this subtract instruction is data dependent on this add instruction. This subtract instruction is data dependent on this add instruction because the add instruction is producing a result R1 which is being used by the subtract instruction. This is our read after our write hazard. The implication of this hazard will be described on the upcoming slide. Well, the other category of data hazards are name dependencies or false dependencies, which occur when two instructions use the same register or memory location called a name, but there is no flow of data between the instructions associated with that name. The name dependencies are further categorized into two types. The first is anti-dependencies, or var hazard, or write after a read hazard. Let us try to understand this with an example again. Note that this subtract instruction is writing this register R2 while this add instruction is reading this register R2. However, there is no flow of data that exists between these two instructions. So this is a write after a read hazard. Well, dear students, var hazards normally occur in out of order execution and their solution is register renaming that can be done statically by the compiler or dynamically by the hardware. The second category of name dependencies is called output dependency or WAW hazard, write after a write hazard. Let us again try to understand this with an example. Well, an output dependency or write after write hazard exists between these two instructions when both try to write the same register or the memory location. As you can see over here, both are trying to write R1. Write after write hazard normally occur in pipeline processors that allow out of order completion. That is, allow an instruction to proceed when a previous instruction is stalled. And a solution to write after write hazard is also register renaming that can be done, of course, statically by the compiler or dynamically by the hardware. One last point I want to mention over here is that you don't have to worry about these name dependencies or the var or WAW hazards in case of an in-order pipeline. That is a pipeline in which the program order is not changed. Well, dear students, raw hazards, that is read after write hazards, are the most common of all. Let me spend some more time on the implication of raw hazards on an instruction pipeline. Consider these two instructions in which you can easily identify the read after a write hazard. So instruction 1 is writing register R1 while instruction 2 is reading. Well, this is a 5-stage pipeline diagram for these two instructions. Note that instruction 1 is writing the result in register 1 at clock cycle 5. At clock cycle 5, instruction 1 is writing the destination register R1. You can also observe that instruction 2 is trying to fetch the operand from register R1 at clock cycle 3 in this ID stage of the pipeline. And it is very obvious that instruction 2 should read the contents of register R1 in clock cycle 6 once it is written by the instruction 1. And if it tries to read the contents of register R1 in clock cycle 3, so it will get the old contents of R1, not the contents which the programmer is expecting after clock cycle 5. So what is the solution? Well, there are multiple solutions to raw hazard, and the most simple is stall the pipeline. And let me show you this in another pipeline diagram. In the clock cycle 1, instruction 1 is fetched. In clock cycle 2, instruction 1 is decoded while instruction 2 is fetched. In clock cycle 3, instruction 1 is executed and we do not move the instruction 2 to the decode stage. And the same thing happens at clock cycle 4 and the same thing happens at clock cycle 5. At clock cycle 5, once the instruction 1 has written the R1 register, now is the time that instruction 2 can read the operand R1. So at clock cycle 6, we have made the instruction 2 read the operand R1 and R5 and move ahead, and finally both the instruction completes at clock cycle 9. So to sum up, we place 3 no operation instruction to stall the pipeline for 3 clock cycles, thus ensuring that instruction read its operand at clock cycle 6. Well, dear students, stalling pipeline is a solution, but it increases the pipeline latency. In your computer architecture course, you will study other better solutions like the operand forwarding, out of order or dynamic execution, which includes techniques like speculative execution, branch prediction, and data flow analysis. Well, let us move on to the third category of hazards, control hazards. Well, instructions that change the program counter leads to control hazards. For example, all branch instructions change the program counter register from executing the next instruction in sequence to some other location. Consider this example. Instruction 1 is a compare instruction which compare the contents of R1 and R2, and instruction 2 is a jump instruction. Jump if equal to this address 1048 or to this label loop. So this jump instruction will change the contents of the program counter if the contents of R1 and R2 are equal or same. Okay, so let us understand this by again an illustration using this pipeline diagram. Suppose this compare instruction is residing at memory address 104. Let's suppose this. And also assume that each instruction takes 32 bits. Well, in clock cycle 1, the compare instruction is fetched. In clock cycle 2, the compare instruction is decoded and this jump instruction is fetched from address 108. And in clock cycle 3, another instruction is fetched from the next address 112. Another instruction is fetched and another instruction is fetched. Finally, note that if R1 equals R2, this jump instruction writes the program counter with the address 1048. That is, the next instruction to be executed should be from the address 1048 and not from the address 112 and then 116 and then 120. But in the pipeline, instruction 3 from address 112, instruction 4 from address 116 and instruction 5 from address 120 are already executing. So what is the solution? So what are the solutions to such control hazards which occur due to branch or jump instruction? Okay, dear students, you will study all these solutions which are mentioned over here on the slide related to the control hazards in your computer architecture course. Let me just name them for you. The first is flush the pipeline by predicting that the branch will be taken or will not be taken. Then is the delayed branch, and then using dynamic branch prediction scheme like a 2-bit branch predictor, correlating predictor, and the tournament branch predictor, we ensure that we do not fall inside the hand of such control hazards. To make you understand, let me give you a bit of idea about flushing of the pipeline. Okay, so let's suppose that this is a situation. The compare instruction has been completed because this is clock cycle 6. The jump instruction is writing the program counter at clock cycle 6. Contents of the program counter to 1048, let's suppose. By this time, these 3, 4, 5 and maybe another instruction 6 are inside the pipeline. If this jump instruction do not execute, this pipeline instructions keep on pumping in and the code keep on executing the way it is right now. But if this jump instruction is a success, that is, this jump instruction has overwritten the program counter with the address of 1048, so that means we need to flush these instructions. I need to flush this instruction, I need to flush instruction number 4, I need to flush instruction number 3, and I need to pump in another instruction from address 1048 and I need to execute it starting from clock cycle 7, and then n+1, that is instruction from 1052 address, and then so on. Okay, so we are done with the pipeline, the concept of pipeline, and the basic hazards, that is the structural hazards, the data hazards, and the control hazards. Okay, so well, dear students, before I close today's session, let me give you a brief but comprehensive comparison of two famous hardware architectures used by CPU designers to design the architecture of their microprocessors: the reduced instruction set computers and complex instruction set computers. Well, consider this basic architecture where we have a memory, register file, and an ALU. And suppose we want to multiply two numbers, one at memory address 5 and the other at memory address 7, and want to store the result at memory address 5. Well, in case of CISC architecture, there exists a single complex instruction that can perform this task in maybe one clock cycle, and of course that clock cycle will reasonably be large enough to execute this complex instruction, or maybe in 70 to 80 clock cycle if the clock cycle is small. So this is what in case of a CISC, a complex instruction that operates on two memory operands directly. Well, dear students, in case of RISC architecture, which is normally load store architecture, the same task is performed using maybe 4 simple instructions. And of course, the clock of a RISC architecture will be far less than the clock cycle of a CISC architecture. Well, my dear students, when you compare RISC and CISC, there is no clear winner, as I will show you on the next slide in a brief comparison. The usage of a RISC or a CISC architecture all depends upon the application and the scenario of use. And this slide gives a comparison of different characteristics of RISC and CISC architecture. The RISC architecture has simple and less number of instructions which are easy to decode and implement. CISC has complex and more number of instructions which are difficult to decode and implement. In case of RISC, the instructions are of fixed size. In case of CISC, instructions are of variable size. In RISC, instructions take only one clock cycle to complete their execution, and in CISC, instructions take a varying amount of clock cycle times, maybe from 2 to 15 these days. In case of RISC, the CPU control is hardwired without control memory, while in case of CISC, the CPU control is micro-coded. The arithmetic and logic operation in case of RISC use only the register operands, as we have already seen. And in case of CISC, arithmetic and logic operation can be applied to both memory and register operands. In RISC, we have more number of general purpose register, while we have less number of general purpose register in CISC. In RISC, we have less and simple addressing modes. In CISC, we have complex addressing modes. In case of RISC, the pipelining is easy to implement, which is of course difficult to implement in case of CISC. The example of RISC architectures are RISC-V, MIPS, ARM, PowerPC, Spark, Alpha, Blackfin, Motorola 88000. Intel i860 and Intel i960 are also RISC computers. While in case of CISC, the Intel x86, which we are studying in this part of the course, is a famous example of a CISC computer. Other than that, PDP-11, IBM 370, Motorola 68000 are all examples of CISC computers. Okay, so that is the end of today's session, my dear students. Hope this session was informative for you all. If you have liked it, please subscribe my YouTube channel and share it with your friends. I wish you all the best. Happy learning and Allah Hafiz.